Hello and welcome to video lesson 2 on shear stress. Our learning objectives for today are to define shear stress, to define single shear, and to define double shear, and to be able to calculate shear stress. So for this lesson, you should be reading Beer and Johnston section 1.2b. Let's talk briefly about the single shear setup. I've got two plates here that are connected by a bolt. And I'm pulling to the left on the top plate, and I'm pulling to the right on the bottom plate, and each plate is subjected to a force of P. Now the bolt is going to be stressed in this red circular area that has cross-sectional area of A. And there's going to be shear stress that develops in the bolt. So what we need to do is we need to take a look at the top part of the bolt. So if we take a look at the top part of the bolt, cut through the red area, and consider the equilibrium of the top part of the bolt, we would find that the internal force V is equal to P. And shear stress is by definition given to us as the force that is acting on this cross-sectional plane here, divided by the area of the cross-sectional plane. And in this case, it happens to be in magnitude P over A. Now, as before, when we were talking about normal stress, the units of shear stress are going to be force per unit length squared. And that would give us the same types of units: PSI, KSI, pascals, megapascals, gigapascals, whatever is appropriate for the stresses in a part. So for the case of the single shear bolt, we would have the shear stress given to us by the general equation, tau is equal to V over A. And in this case, the specific instance equals P over A. Now, we also have connections in machinery and in building structures quite often that look like this, where we might have a gusset plate sandwich, and our member is in the middle of the gusset plate sandwich. And in this connection, we'd have something called double shear. Now, the force carried in the tension member here would be what we will call P. And that means that each plate here is going to carry P over 2 in support reaction the other direction on the assemblage. And our bolt itself is going to have two shear planes. It's going to have a shear plane between the top gusset and the tension member, and it's going to have another shear plane between the tension member and the bottom gusset. So once again, we would need to consider the equilibrium of the top part of the bolt. And if we consider just this shaded top part of the bolt, we would have a force of P over 2 on the bolt. And that would mean that through the plane that we would cut through between the plate and the tension member, we would have an internal force develop of P over 2. So we would apply the basic equation, tau equal to V over A, to define shear stress. And that's going to give us tau is equal to P over 2A. So bolted connections are twice as strong in double shear as they are in single shear. So let's take a look at a calculation example. And in this bolted configuration, we know that the allowable shearing stress in the bolt is 350 megapascals. So we need to determine the minimum diameter of the bolt. So what is the smallest diameter of bolt that we could use and this configuration perform as intended? So this is actually a case of double shear. And we would know that because we would have two shear planes through the bolt. We're going to have one shear plane through here. And we're going to have another shear plane through here. And the top part is going to be subjected to 100 kilonewtons of tension or force. And then the bottom part here, the bottom gusset plate, is going to be subjected to 100 kilonewtons of force. So 200 kilonewtons of force in the tension member, and then in each gusset plate, we're going to have a bearing of 100 kilonewtons on the bolt. So then we would need to take a look at the top part of the bolt. And what we would see is the bolt is going to be subjected to 100 kilonewtons like this, and then 100 kilonewtons through the cross section that's being sheared. So it's a case of double shear, and as expected, V is equal to P over 2, which would give us 200 kilonewtons divided by 2, or 100 kilonewtons that each shear plane has to transmit. So we're going to use the general formula that tau is equal to V over A. And then the minimum area, when we solve for the minimum area and plug in the allowable shear stress, we would find that A minimum is equal to V over tau allowable. So we need to just plug in the numbers that we've got. We know that V is going to be 100 kilonewtons, or 100 times 10 to the third newtons. And then the allowable shear stress is 350 megapascals. So that would be 350 times 10 to the sixth newtons per meter squared. Well, the newtons are going to cancel out. The meter square in the bottom is going to flip up to the top, and we're going to have a result of 2.86 times 10 to the negative fourth square meters for the required bolt area. Well, that's related to the diameter. Area is equal to pi d squared over 4. So when we solve that for the minimum diameter, we end up with the minimum diameter equal to the square root of 4 times the minimum area divided by pi. And that's equal to the square root of 4 times 2.857 times 10 to the negative fourth square meters divided by pi, the same result that we had there. And the minimum diameter would be 0.0191 meters, or 1.91 centimeters. That concludes video lesson number 2 on shear stress.